All right. So last class, we started to dig into the ambiguous case. So when we used our law of sines, which the setup would have been for sine beta over B equals sine alpha over A. So we ended up with that expression for beta. And then when we put it in the calculator, we ended up with 49.9 degrees. But when we looked at the picture as drawn, beta appeared to be larger than 90 degrees, but the number we got was smaller. So when we click does not seem reasonable, down at the bottom here, we see an actual drawing where that 49.9 would actually go. And then there's a finish it button, and the finish it button actually shows you the two different triangles. So normally when we draw a triangle, we draw the triangle to look like the figure on the right, the 35 degrees, the 8, and then the side length 6, A, is pointed outward. We don't normally draw this wonky obtuse triangle as our like default triangle. But some triangles, especially when we have this angle side-side setup, this ass situation, have the possibility of a second inner wonky triangle. Now, when you're looking at how do these two stupid triangles relate, so the 35, the 8, and the 6 are the same in both triangles. The 49.9 that we got, so let me find my annotate button. So on our bottom right figure, that 49.9 is in the outer triangle. But when we swing that 6 side in to make the inner wonky triangle, it also creates this isosceles triangle. So where the two side lengths are 6, the opposite angles have to be the same size. So that's why this other angle over here is also labeled beta, because it is also 49.9 degrees. Now, it's not really beta in our like ABC triangle, but it is the same size as the beta for the outer triangle. Now, when I look at my beta prime, because that's what we label all the angles on the inner wonky triangle, all of them get this prime mark. So beta prime here is 180 minus beta. So 180 minus the 49.9 gives us a beta prime value of 130.1 degrees. So that's where the second number for beta prime came from. So our original beta was 49.9. And then I know two angles in the triangle, so I could subtract from 180 to get my original gamma. And then you notice, like in this, of the two triangles, the triangle on the right, gamma here, 95.1 is bigger than 90. So this picture is not drawn to scale. But if we drew it to scale, then the triangle on the left gets like even wonkier and tinier, and it's really hard to write any numbers down. So when you're dealing with law of sines, law of cosines triangles, you kind of have to accept like they're not going to be to scale. You can't really trust whether the angle is bigger or less than 90 based on how the picture looks. You have to go with what the numbers tell you. So we're actually going to practice running through this whole calculation, but this is just like an initial look of here's how a two triangle situation like looks when we finish it. There's a picture of the two triangles. So on our next slide, we've got four cases for the ambiguous case. So when we have this angle side-side setup, there is actually the possibility of having no triangle at all. So you can have your angle A and your side B, and if side A is too small, it's this setup where I have angle A and B, and then A is like, I can't reach. I'm trying, but I just don't make it. Now, the way we figure out this height is by using right triangle trigonometry. So if I actually continue A, the direction of A, because it's hanging perfectly down, that makes a right triangle. And my sine of A in the right triangle would be this height over B. And then I could solve for height, and that's where I get B sine A. So B sine A is my minimum required height to make a triangle. Now, if my A perfectly equals B sine A, then I make one right triangle. So there's my minimum guy. If A equals B sine A, I have one nice right triangle. And how often do you think that actually happens for this homework? Never. It's too nice. But it does give us that minimum. The never, I don't think it happens in the web work just because it feels like a cop-out. Because if you don't pay attention, you'll do more work and you get like a negative number coming out of the law of sines. And like if you get a negative number, that's a sign you either screwed up your math somewhere, or if you had an ask situation, it's a sign that it wasn't a triangle to begin with. Now, our other two cases, the two triangle case is when our A value is bigger than the minimum required height, but isn't as big as B itself. So typically when we're looking at our setup, if A, the side opposite angle A, is smaller than the other side, then we have two triangles. If A is bigger than that other side, then we only have one triangle. So we're usually just focusing on the last two to figure out, is it two triangles or one triangle? Just because we don't normally see the first two setups, but they can technically occur. All right. So now we're looking at what do we do when we have an ambiguous case? So what do we do when it's an ask setup? We're going to figure out what B sine of A is, just calculate that, and then we're going to compare our opposite side to this number. If it's smaller than that, no triangle's done. If it's equal to it, one right triangle, and we're almost done. We'd still have to figure out like one more side and one more angle, but if it's bigger than B sine A, but not as big as B, That's our full ambiguous two triangle case. If A is bigger than B, then we'll only have one triangle. So it really comes down to, is A smaller than B or is A bigger than B? Because on the homework and on the test, we don't typically give you the case where it'll be one or no triangles. So here we're reusing values from slide 6. So in slide 6, let's just sketch in those labels again. So angle A here is 40 degrees. Side A is 3. And side B is 2. So remember when I first labeled this, I was like, I usually put B here on the diagonal left side. I do that because this is how we normally see the ASC setup. It's angle and then the two diagonals are the sides. So B sine of A is 2 times the sine of 40. So we get 1.286. So do we at least have a triangle? Yes. A is bigger than 1.286. So there's our, is there one triangle? Yes. It's definitely bigger. Is it a right triangle? No, they're not equal. So are there no triangles? It's not less than, so no, there is at least one triangle. Are there two triangles? No, because A is bigger than B. So this is the situation where there is exactly one wide triangle. Now remember, when we first looked at this setup, we were talking about the size of the angles in comparison to the size of the sides. And we noticed that since B is smaller than A, angle B is smaller than A. So when we had this setup where A is larger than B, this means angle A is also larger than angle B. And this makes it one triangle. Because we don't have the possibility of B being bigger than A or really bigger than A. It's only smaller than A for the angle. So we already calculated this full triangle on slide 6. We're not going to do the calculation again, but this is just showing we already dealt with one ASC scenario and realized it was just one triangle already, just using our knowledge of how angles and sides have to work in the triangles. But if we get the case where A is smaller than B, that's where we've got to argue and do the full triangle craziness. All right, so now we're actually working with that two triangle setup. So our first step is to draw the picture. So when I draw it, I draw my first diagonal side as longer and my second diagonal side is shorter. Because my assumption is it's going to be an annoying two triangle setup. So I just like my picture to look like that to start with. And my given angle, they called it A. So I put my A here, label it 35 degrees. And then side A is 6. And then side B is 8. So that means down here, we've got angle B. And then our last two are going to be C's. So here, the slide is telling us to figure out what B sine A is, so we can figure out if we have at least one triangle or two triangles or only one wonky triangle. So B sine A is 8 times the sine of 35. 8 sine 35 degrees. I'm still in degrees. 4.5886. So 3 decimal places will be 4.589. 4.589. So our A value is bigger than 4.589. So we definitely have at least one triangle. And our A value is smaller than our B value. So this is the two triangle setup. Now we've got a giant table with 12 entries where we're going to fill in all the things. Now we actually know right now angle A is 35. So that is 35 for A and A prime. They just listed all the angles and sides with primes. But the things that we know from the get-go are the same in both triangles. Side A is 6 and side B is 8. So those are our givens, just filling those back into this ridiculous looking table. So now we're going to come back up here and we're actually going to solve for angle B again, because these are the same values that we had before. So the sine of B over B equals the sine of A over A. So sine B over, whoops. Over 8 equals the sine of 35 over 6. So B is sine inverse of 8 sine 35 all over 6. We got some extra parentheses to drop in there. Now we need, it says round all values to one decimal place. So inverse sine 8 sine 35 close divided by 6 close. 49.88, so 49.9 degrees for B. Now that I have B, I can figure out C. C is going to be 180 minus A and minus B. So C is 95.1 degrees. So we've almost solved the outer big triangle. The last thing is just to calculate side C. So I'm going to do that in my second blank here. So that'll be C over the sine of C equals, and I always go back to my A over the sine of A. So it'll be C divided by the sine of 95.1 equals 6 over the sine of 35. And we'll multiply by the sine of 95.1. So 6 sine 95.1 close divided by sine 35 close. So 10.419, but we rounded to one decimal place, so 10.4. But biggest angle, 95.1, biggest side, 10.4. Those are a pair. So yes, this is following my size of the angle, size of the sides. All right, now we're going to figure out the wonky triangle. So I'm going to draw a picture of that. But I'm also going to sketch in that extra original side. So remember, this is 49.9. And then this angle is also 49.9, the outer one. So our beta prime, or B prime, I should say, because we just used ABC. B prime is 180 minus B. So that's 130.1. I'm going to fill back in the rest of the thing. So we did know B was 8. A is 35. And side A is 6. And now we're going to focus in on C prime and little c prime. So for angle C prime, that'll be 180 minus A minus B prime. That's just taking our two angles that we know, the 130.1 and the 35, and we're going to subtract that off of 180. So we get 14.9 degrees for C prime. Now, our last step is to figure out side C prime. So I'm going to have C prime over the sine of C prime equals, and I always go back to my A's, so little a over the sine of angle A. And now we multiply by that sine of 14.9. So C prime is We're going to run that calculation. 6 sine 14.9 close divided by sine 35 close. And now our C prime is only 2.689, which is 2.7. All right, so in WebWork, we have one question that does the ambiguous case. The question itself, though, is a little buggy. So for most of y'all, you're going to type in the big triangle for the first set of answers, the small triangle for the second set of answers, and it takes that and it's happy. Sometimes, though, you're going to type in those answers and it's going to be like, no, your answers are all wrong and I hate you. When that happens, try swapping all of the answers. So your answers on the second triangle, put those on the first, and then take the ones on the first triangle and put those on the second. That sometimes fixes the bug. If that doesn't work, hit email instructor button and I will go in and argue with it and punch it, and worst case scenario, give you credit for the question. So when you are working this is problem 4 on section 5.1, the ambiguous case. And it's real obvious because all the ones before it, there's only 3 blanks. And then you get to this one and now there's 6 blanks and you're like, oh, here it is. The programming behind the question wants whole number angles. Like the way they programmed the question is very stupid, but basically you'll get like 42.9999 degrees. They want you to type 43 degrees, and then they want you to run the calculations with 43 degrees. But if you run the calculations with 42.9999, then your side lengths are a tiny bit off, just enough for the program to be like, nope, it's wrong. So that's the other trick on this problem is if it's saying all of your angles are wrong, but you notice your angles are really, really close to an integer, round it up and run the calculation with the integer number. Like that's the why it screws up. Yeah. Okay, one sec. All right. So questions on what we did here, how this all shook out. Now, in the past, we have put a 2 triangle question on the test. What we did to try to save some space, though, is we asked for all the dimensions on the outer triangle. And then on the inner triangle, we only asked for the angles. So you didn't have to do this last C calculation. But that doesn't really save that much time. So like we've been going to just doing 1 triangle. So we'll see what happens. But basically on the test, like draw the figure, see if the A value is smaller than B or bigger than B. Figure out if that means your B is going to be small angle, in which case it's 1 triangle, or if B is larger than A. So in this one, since side B is larger than A, angle B is larger than A. And if you look at both of our triangles, angle B is larger than angle A. It's just our first triangle, it's a little bit larger, and our second triangle, it's ridiculously larger. But if you look at our side lengths in our second triangle, the angle for C prime was 14.9 and the side was 2.7. That was the smallest angle and the smallest side. In fact, that second triangle is real tiny. All right, let's see where it goes from here. Oh, an application question. Yes, that was sarcasm. All right, so this is one of the ways you can measure how high something is. So a surveyor takes two sightings of the peak of a mountain 900 meters apart on a direct line to the mountain. So they have this tool that like sits on a tripod and calculates the angle of elevation. Like you know, it's kind of like using a telescope. You zero it in on the top and like say, all right, read the angle, and it says, all right, here's the angle. And then you walk backwards 900 meters, set the tripod up again, point it. All right, now what's the angle? So it gave these two angle measures. And we know that the height of the tool is 2 meters high. So we're going to have to use that 2 meters at the very end of the problem. But we have here a figure of the weird triangle situation. So there's a 47-degree and a 35-degree angle. But the side length I know is 900 meters between where the two angles were taken. So we did this before when we were dealing with right triangle trigonometry. And there is a way to just deal with right triangles and figure this out, but it gets kind of hairy. We can also use the law of sines and just focus on this dashed outer weird triangle. So that's what I'm going to draw in my picture here, is we've got those two measurement points and then that wonky angle. So I got 35 degrees there. I got to call these something. So point on the left gets A, point on the right gets B, last guy gets C. So I don't know side A. I don't know side B. But I do know side C is 900 meters. In order to use law of sines, I need to figure out what angle C is. So when I extend my horizontal, that other angle measure I got, the 47 degrees, goes right here. So that's not angle B. Angle B is the angle inside the triangle. So B is going to be 180 minus 47, which is 133 degrees. And then that means angle C is going to be 180 minus 133 and minus 35. So that's 168, so 12. So C is 12 degrees. Very tiny. Now I want to figure out the height. So to figure out the height, I'm going to use a right triangle. I know the angle, I know the height. If I can figure out the hypotenuse of one of those right triangles, I could use it to find the height using right triangle trigonometry. So I'm either going to find side A or side B. It doesn't matter which one we want. Like both of them will give us the final answer. I usually just like default go for A. So A over the sine of A equals, and then C is the one that I know both of them. So side C over the sine of angle C. So A is my unknown divided by the sine of 35 equals C is that 900 meters divided by the sine of 12. So we're going to end up multiplying by the sine of 35. All right, so 900 sine 35 close divided by sine 12 close. And it's a big number. 2,482.875. Now that is not the height. That is just side A. So since we found that right diagonal, I copied the right diagonal triangle, which had a 47-degree angle, the number we just calculated, the 2,482, and what they called height. Like I put height here. Technically, we're going to have to add 2 to our answer at the end because of the height of the tool, but this is our right triangle that we're going to calculate with. So H is opposite, and the 2482 is the hypotenuse. So my trig function that uses opposite and hypotenuse is the sine function. So I'm going to use the sine of theta as opposite over hypotenuse. So we're going to have the sine of 47 degrees equals H over crazy number. So H is going to be crazy number times the sine of 47. All right, so crazy number still in my calculator times the sine of 47. So I get 1,815.86, but, and I'm out of room, so I'm going to put this on the side. We got to add 2. So we actually get 1,817.86. Now let's see what they said for rounding directions. Oh, well, they wanted angle C first, sorry. 12. Wrong angle C. 133. They labeled their triangle different than I labeled mine. So their angle C was what I called B. Their angle A is what I called C, so that's 12. Ugh, they did the calculation different. All right, so give me a sec. I'm going to run the numbers the other way. 900 sine 133 divided by sine 12. So this rounds to 3166. Ugh. Sorry, they actually want, is it 1818? No. Is it 1817? There. Ugh. So this is the problem with carrying so many decimal places. Like it messes with the answer. So our final calculation would have been this 3165 number times the sine of 35. Yeah, it should be taking 1818, sorry. I programmed it badly. Like I tried fixing it and this problem annoyed me, so it didn't fix as well as I would have liked. Whether we got the programmed answer is immaterial. Did the way we worked with the law of sines triangle there to find one of the two diagonals, and then we used the diagonal and the sine of theta to calculate the height and then added 2, does that make sense? Like you could think it was the +2 that really threw this whole thing off. All right, now there is one other formula. We don't use it that often, but when you have a non-right triangle and you draw in the height, if you know angle C, so if this is angle C, then the other two sides are A and B. So if I know two sides and the angle in between them, if I use my trig function with sine of C would be the height over side A, and we solve and we get A times the sine of C. Then my area of a triangle is 1/2 base times height. Well, my base is B. My height, the thing perpendicular to B, is what I just solved for, A sine C. So we get this formula. So the area of a triangle is 1/2 side A times side B times the sine of angle C. So if I know two sides and the angle in between, I can figure out the area of that triangle. Just using my sine function in there and the 1/2 that comes from our normal area formula for a triangle. So we've got AB angle C. So area 1/2 AB sine C. A is 8. B is 6. Sine of C is 30 degrees. And then we just crunch, crunch, crunch. And we get 12. Because the sine of 30 is 1/2. We get a dancing triangle. I don't even remember if this formula shows up in the homework. It's just more of a like, here's a formula for the area of any triangle if you know two sides and the angle in between them. Now, if we had this setup, two sides and the angle in between, we could not use law of sines to solve this triangle because law of sines requires us to have an angle and the side opposite it as a pair. It is a setup that determines a triangle. We just would have to use a different formula to figure out what side length C is. All right, so we got one more application question for law of sines. This one is in WebWork. So, to determine how far a boat is from shore, two radar stations 435 feet apart, find the angles out to the boat. So, the radar stations are actually sending out like a whole wave of signals, but they get a ping from a particular direction, and then they measure the angle for that direction back to the angle to the other station. So they get this 70 and 60 degree angles that we see in the figure. The 435 feet is the distance between them there. So the first thing they ask us to determine is the distance of the boat from station A. So from station A to the boat, that is the side opposite radar station B. So they're asking us to find side B. But if I try to write like A over sine of A, I know angle A, I don't know side A. So I need to calculate my third angle because I'm going to have to use angle C and side C to finish my law of sines. But we know how our angles work. 180 minus the other two. So C is 50 degrees. So our unknown B divided by the sine of angle B is 60 degrees equals side C is that 435 they told us. And then the sine of 50 degrees. So we're going to multiply by the sine of 60 on both sides. And now we got something we can crunch. 435 sine 60 close divided by sine 50 close. So side B is 491.7744 blah, blah, blah. Round to the nearest foot, 492. All right. Now they're saying, determine the distance of the boat from shore. So in all of our previous solve the triangle questions, the other thing we'd be solving for is the third side of the triangle. But is the third side of the triangle, the distance from the boat to radar station B, is that the distance from the boat to the shore? No. So when they're asking us to determine the distance from the boat to the shore, that's something we need to draw into the figure. So I draw straight from the boat to the shore, and distance makes a 90-degree angle. So now that I know my side length over here is 492, and I know my 70-degree angle, I can figure out my height using my sine function. The sine of 70 is the opposite side h over the hypotenuse of that left-right triangle, 492. So h is 492 sine 70. So that times the sine of 70 gives me 462.11, 462. We get a very happy dog. All right, so questions on how this other application question shook out with the law of sines. All right. What I'd like to do next is go practice another one of the ambiguous case. So I'm going to go pull my numbers for problem 4 from 5.1, unless anyone has already tried that problem and has run into problems. Like if you would like me to work with your numbers, I can do that as well. So let me see. So they labeled the angles stupidly. All right, yes, this is a 2-triangle problem. So let me flip the share. So this is 5.1, question 4. All right, so instead of using A's and B's, they went with B's and C's. And if we try to use the picture they gave us, it gets really weird. Like I can't do these triangles unless I draw them the way I showed you guys, which is the angle they gave us in the bottom left, a long side, a short side, and the flat bottom. So since they gave us angle B is 67 degrees, so that's the angle. The side opposite that is a ridiculous 5.53061. So that is side B. And then the other one they gave us was side C was 6. So that means angle C is down here on the bottom right, and then our A's are our leftover sides. All right, so whenever you see a number this stupid looking, 5 decimal places, they are trying really hard to make your first calculation be an integer. It doesn't actually work very well, but they're trying. So the first thing we're going to calculate is what they're calling angle gamma. But I'm just going to stick with the capital letters. So the sine of C over C equals the sine of B over B. I don't know C, but I know side C is 6. And then it'll be the sine of 67 divided by 5.53061. And we're going to multiply by 6. And then we're going to apply our inverse trig function. Now, make sure you're in degrees for this calculation because the sine is 67 degrees. So this is going to come out as a degree number. I'm saying that mostly to myself because in my calculus class I was in radians. But inverse sine 6 sine 67 close divided by 5.53061. So 86.99972. So you see what I mean by it's really, really close? So what they actually want us to do is to type 87. So if I type in 86.99972 and check, it took that. But if I delete it and type in 87, it also takes 87. That little bit of decimal difference in our calculations, if we keep using the 86.99972, it's going to throw our other calculations off. So even though the 87 is less precise for the way WebWork is programmed on this particular problem, I'm going to actually run the calculations with the 87. But notice in our original setup, side C was 6, side B, 5.5, is smaller than side 6. So C has the potential to be, or C is bigger than B. So that means we've got 2 triangles. So we're still solving the outer triangle right now. I just finished angle C. Now I'm going to go back and figure out angle A. So A is 180 minus 67 and minus 87. So A is 26 degrees. And now I'm going to calculate side A from the sine of A, and I'll use the B's. $5.53061, because of course. So we're going to multiply by the sine of 26. So 5.53061 sine 26 close divided by sine 67 close 2.633837. So angle A, we got 26. And side A, 2.633837. All right, elect both of those. So now we're going to come back and do the second triangle. So our original angle C was 87 degrees. So our C prime, which is gamma prime, is going to be 180 minus 87, which is 93 degrees. B is still 67. And then angle A up here is going to be 180 minus 67 and minus 93, which gives us 20. So now to find side A, we have A over the sine of 20 equals B over the sine of 67. Yeah. Sorry. B is the stupid decimal, 5.53061. And sine of angle B is 67. So we just got to type that horrible calculation in. 5.53061 times the sine of 20, close the parenthesis, divided by the sine of 67, close the parenthesis. 2.054937, blah, blah, blah. All right. So our gamma prime was 93. Alpha prime was the tiny 20. And then A prime, 2.054937. There we go. And it took those answers. So let me just real quick label those primes. So this is technically A prime. All right, so the tricksy stupid catch on this one was our first angle was really, really close to an integer. So we just turned it into that integer, and then we used the integers for the angle calculations on all the rest. Now on the test, it's not going to be an integer angle. Just use whatever the angle is with like 3 or 4 decimal places and just run the calculation with that, and it's fine. But that's the like buggy nature of this problem. Oh yeah, I could put this away. All right, so what I want to do next, unless someone has a burning question, is I just wanted to look at a few of the word problems just to discuss how to draw the picture, how to set it up, because I do get these questions quite a bit. particularly problem 7, but also sometimes problem 8. We did 5 and 6, we did examples similar to those. So there's one where you're like determining the height of the mountain. So it'll be a similar kind of drawing. And then the other one is the boat problem we did with the 2 radar stations. So these are the other 2. So this one is kind of similar to the boat problem. We've got 2 radar stations again, but we've got this satellite in orbit. Now, if you look at the picture, the line from B to the satellite almost looks straight. And if you look at the angle, it's supposed to be 86.2 degrees. So like it is close to 90 degrees, but it's kind of hard to see like which side is which. So what I do with this is I redraw the picture. So I put A here, B here, and I put the satellite way over here. So now when I label that 86.2 degrees and the 83.9, like now it's a little easier to see that 86.2 is not inside our AB satellite triangle. It is outside the triangle. Now the question asks for 2 pieces. They ask how far is the satellite from station A, which would be from our labels side B. And then they ask how high is the satellite above the ground? So if I drop a height from my satellite, once I calculate side B, I'm going to redraw the outer right triangle. So when I have side B and my angle of 83.9 degrees, I can just use right triangle trigonometry. The sine of 83.9 degrees has to equal h over b. So h equals b times the sine of 83.9. So that's why it asks for 2 results here. And then they said round to the nearest whole mile. So not working the whole problem, but just redrawing the picture so it's a little easier to see where the numbers are and talking about what the question is asking you to find. So does the setup on this one make more sense, like where the pieces are going? But yeah, I do get questions on this figure, and I agree, it is a bad drawing. Like that satellite really should be more to the right just to see the figure correctly. But it turns out if we calculated the distance from B, like the distance, all of these vertical, the diagonal and the height, they're going to be kind of close to each other because those angles are pretty big. Now our other figure, we've got a plane flying over the ground. This is a relatively small frame of reference, so we assume the ground is flat, ignore curvature of the earth. So this pilot is flying over a straight bit of highway, and he sees 2 signs on the highway. So sign A and sign B. And we know that the distance between these 2 signs is 4.3 kilometers. So in our figure here, that's 4.3 kilometers. So the 32 degrees and the 56 degrees are angles of depression that the pilot looks down to see the 2 positions. What we're going to use is the knowledge of parallel lines being cut by a transversal. Now, it's been a while since you've had to do this. This is very much a geometry bullshit thing. But I drew in the 2 parallel lines, and then I drew one of the diagonal lines in. And you see how that makes like a backward Z shape? So in our backward Z shape, those 2 angles in the Z are the same size. So this 32 degrees up there is going to be 32 degrees down there. Now there's a second wonky Z for the 56 degrees. So there's where our angles actually show up on the ground versus where they showed up for the airplane. Now the question here is asking for the distance of the plane to sign A. So sometimes I mark my unknowns with stars, but that's the thing we want to find, which is opposite side B. So I would call that little side B. But there is enough information to figure the rest of this out, figure out all the angles in the triangle, and then use law of sines. So I'm going to leave the rest of that for y'all's homework. But I just wanted to go over the figure and how we use the two numbers they gave us, where they show up in the rest of the figure, because the whole parallel lines cut by a transversal, like that's so far in the past, it may not be as readily like, oh yeah, that's a thing. But hopefully now that I doodled it, you're like, oh, okay, yeah, I vaguely remember that was a thing once upon a time. I'm just the weird math teacher that remembers the actual name of the situation. All right. So even our stupid buggy law of sines question, like we figured it out, use whole numbers for the angles, and I think that should actually like save a lot of the headache on that one. All right. Well, we're done a few minutes early, but I'm gonna stop the recording.